Okay. My name is Christian König. I'm working for AMD for something like 8.5 years now. I'm one of the maintainers of the AMD and Radeon kernel module, AMD GPU and Radeon kernel module. And for the last 2 years, I'm also maintaining TTM. And that's what I want to talk about. So this presentation is all about the TTM memory manager in the Linux kernel. What's TTM? TTM is a manager for GPUs with dedicated video memory. So if you got something like an AMD GPU or an NVIDIA GPU, both Radeon, AMD GPU, as well as Nouveau, are using TTM to manage their buffer objects and to move their buffer objects around. The acronym TTM originally stands for Translation Table Manager, but by today's standards, that's as inaccurate as it could be, because TTM is managing quite a bunch of things, but not translation tables anymore. It used to manage translation tables for AGP, so that's where that came from. Yeah, as I said, TTM is directly used by AMD GPU, Nouveau, QXL, Radeon, and VMware Graphics. And the guys from VMware Graphics, original Tungsten Graphics, are the one who originally wrote it and merged it into the Linux kernel. Additional to that, TTM is used indirectly through the VRAM helpers by AST, Box, HiSilicon, MGA 200, and the Virtual Video Box video driver. So, how does TTM work? First of all, TTM defines so-called memory domains. Since it's managing the local memory on your graphics hardware, the first thing that TTM defines is the so-called VRAM domain. That's representing your memory on the GPU. Then you got the system domain, which is system memory which is mapped or available to the GPU or accessible to the GPU. So the GPU can directly write over a PCIe DMA to the buffer objects in the system domain. And the last thing is the swap domain. And in the swap domain, that's what's not directly accessible by the GPU, but still backed by system memory. So the CPU could write and read from it, but not the GPU anymore. And stuff in the swap domain can, in theory, also be swapped out to disk if necessary. Those yellow dots, or maybe orange, those orange dots here are buffer objects which are allocated and then backed by memory in the different domains. And the important thing in TTM is that those buffer objects can move from one domain to another. So, for example, if you suspend your laptop, buffers from the VRAM domain usually move to the system or swap domain for the simple reason that the local GPU memory the power is turned off. So if you wouldn't evacuate those buffers, you would get just random stuff on your screen or just a black screen if you turn the laptop on again after a suspend resume cycle. So that's what those red arrows here are good for. When applications then use those buffers, they usually move back into video memory or system memory. And that's what the green arrows represent on this slide. How does eviction work? Yeah. First of all, eviction is a process of making room in a specific domain. So, for example, if you have a lot of applications which allocate video memory, you're sooner or later going to run out of that. So what TTM does, it looks at the linked list of buffer objects in your video memory domain and starts to evict things from that domain. So it moves things in other domains, usually the system domain. If there's not enough room anymore, it also moves on and moves stuff into the swap domain. Eviction works by locking the LRU, then picking the first entry on the LRU and calls back into the driver to test if eviction is valuable. For example, in video memory, you usually have a part which is CPU accessible and not CPU accessible. And so the driver can decide if it needs only CPU accessible video memory, that an eviction might not be valuable to actually do. So it's skipped anything. Then we actually evict the barrel, so move it to another domain. And then we retry the original allocation which failed in the first place. And if that succeeds, the algorithm ends, and otherwise we repeat from the beginning again. This is actually rather inefficient, because when we, for example, have a lot of BOs on the beginning of the LRU list, we test over and over again if they are valuable to evict. And that actually doesn't make much sense, but more on that later. Other functionalities that TTM provides. A big functionality when you want to move buffer around is that you need to make sure that nobody is accessing that buffer. When the kernel moves a buffer from A to B, you need to make sure that neither the GPU nor the CPU is still accessing A and writing changes to A while the thing is copied to B. So for that, we have the CPU page fault handling in TTM. That works by TTM tracking at which memory location, which virtual address location buffers are mapped into user space. And as soon as we want to move a buffer around, those mappings are invalidated. And if, for example, the CPU tries to access this memory by writing or reading from it, we end up in a page fault handler. This page fault handler can then identify which buffer object is meant to be accessed by the CPU and wait for that buffer, for the move of that buffer object to finish. That's what the CPU page fault handling is doing here. The other big functionality is the DMA memory page pools. The DMA memory page pools also originated in the AGP days. So on AGP, graphics hardware original could only access uncaged system memory. Now, uncaged system memory is something rather unusual, because when you want to access something fast with the CPU, you usually want to have it caged, so that one read doesn't result in tons of memory transactions. So, but making system memory uncaged is actually a rather costly process. You first call into the Linux kernel, say get free pages to get a free page, and then you change the memory, the caging attributes of that page, which requires a system-wide TLB flush of the kernel page table. And that can take quite a while. So what the memory page pool does is, when those pages are freed up, they're not changed, their caging policy are not changed back immediately, but instead we put them into a pool. So on next allocation, we can serve from that pool instead of asking the operating system, the core operating system, for free pages. Later on, that was the first idea of how AGP worked. Later on, this was extended to provide uncaged write combined pools for modern hardware, for PCI Express hardware, as well as decrypted pages, as well and huge page and DMA 32 page handling. DMA 32 page comes into play when you have older graphics hardware which can't address all system memory. Yeah, as I said, TTM is, the whole framework is roughly 11 years old, nearly 11 years old now. It was merged upstream in June 2009, if I remember correctly. So it has quite a bunch of history. And with that history, it also acquired quite a bunch of problems, which I want to outline and discuss how we started on solving those problems and what else we should probably do to clean that up quite a bit more. The first problem is that after TTM was merged in the upstream Linux kernel, it quickly became a dumping ground of driver-specific features. So whenever a driver maintainer had a feature which he wanted to implement, he just implemented it instead of his driver, he put it into TTM. Because the assumption was that somebody else could sometimes make use of that. Usually that's probably a good idea in open source software. The problem here is that everybody did that without a central maintainer which actually filtered out which features were useful and which features were not useful. So what happened is that TTM became, as I said, a dumping ground. And as we later will see on the next slide, it was rather hard to move to revert that and move functionalities back into the drivers again. The next bigger problem is that we have a DMA, that we actually abuse the DMA API in TTM. So when we ask a core operating system, as I said before, we have those page pools. And when we ask the core Linux kernel, the core operating system, to get us a free page, we always get caged system memory. Changing those attributes of those pages is actually completely x86 specific. And that is also the reason why the ATP backend in TTM always only worked on x86. There used to be AGP hardware with PowerPC, for example, but as far as I know, we never got that working with AGP backend in TTM. Additional to that, those page pools make assumptions how the DMA API works internally. This then works together with things like IO MMU, where you have an MMU block, a memory management unit, in the source bridge, which also maps your DMA address coming in from the graphics hardware into the physical system address. So, third item on my list here is that TTM has a horrible mid-layer design. And there are things where TTM calls driver and driver calls back into TTM. And also there, at the very bottom of this is a functionality which tries to limit system memory usage for processes using the graphics hardware, which are actually implemented from the wrong side. So let's see how we tried. Yeah, as I said, I'm one of the TTM maintainers for 2 years now, and during that time we started to try to fix those problems a bit up. What you see here is the lines of code which the Linux kernel used for the TTM subsystem. As you can see in the beginning, please note the scaling on the left side, it's not that bad. As you can see in the beginning, when we took over, we continued developing new features for TTM and merging that into the upstream Linux kernel. And so the code base first started to rise a bit, and then some of our developers started to ask why we have this function here. Who is using that? And then we got around, so nobody's using that. Somehow we forgot to clean up things in roughly 10 years. So from one day to another, we removed 13% of the whole code base. That was quite a bit. Well, it wasn't full unused code, but it was more like a bunch of features which were used by only one drivers. VMware Graphics had a huge bunch of those which were in TTM, but we could just take them and move them around. That was roughly 2,000 lines of code. And as well as features in Radeon as well as AMD GPU, which were only used by those drivers. And since we are also the maintainers of those drivers, it was relatively easy to move those around. Problem here is we still have features which are only used by, for example, Nouveau. And Nouveau actually doesn't seem to implement them correctly or doesn't seem to use them correctly. So I am trying to sync up with the Nouveau guys to actually get on a page what we should do with that. Either we move it into Nouveau, or what else we need to do. My colleague Wei Huang did a talk about bulk moves in TTM. That's a feature we did late last year. And this is a little bump here at the end, which is like, I think something like 100 lines of code which got added for the bulk move features. And later on, we cleaned up a bit of stuff we actually didn't use. And so we got down with the line of code count quite a bit again. But I think something like 5% of the whole code base could be removed without losing much functionality. Usage of the DMA API. What you see here is the organization of those page pools. So you have a page pool for normal system memory, which has, again, normal caged pages, normal uncaged pages, normal wide combined pages. Then you have a pool for DMA 32, caged page, uncaged, and so on. And those page pools are actually quite important for quick application startup and good performance, because, as I said before, changing the caged attributes of memory takes time and takes a lot of time, especially for if you don't use huge pages. If for those who don't know that, the Linux kernel distinct between normal pages, huge pages, and sometimes called giant pages. Normal pages are on x86 4 kilobyte in size. Huge pages are 2 megabytes in size, and giant pages are 1 gigabyte in size. So if an application happens to allocate 1 gigabyte at a time, you can actually end up getting a really big block of memory, 1 gigabyte, and not just thousands of small 4K allocations. Makes the whole thing much, much more efficient because you have not so much housekeeping overhead anymore. So what's abusing here? The problem is this whole implementation is completely x86 specific. So we had a really hard time getting it working on PowerPC as well as ARM. Some, let's call them desperate Chinese guys even try to get our driver working on the MIPS architecture. And we are telling them over and over again that they have platform coherency issues, and they don't really want to listen to that. So that's also one of the problems which end up in this domain here. Solution to that is moving the whole pooling concept into the DMA API. The DMA API already has a concept of pooling pages, of pooling coherent memory allocations. The problem is it doesn't have a concept of uncaged and wide combined memory. So I've actually already synced up with Christoph Helwig, one of the core Linux developers in that area, that he wants to provide us with a bunch of new flags to make those move those allocations back into the DMA API. And when that's done, we need to implement memory management callback in the DMA API pools, and that will probably solve this problem. When you look into the pooling code, there's a comment at the top of the file that this should probably be part of the DMA API and not be part of TTM. And this comment is sitting there for over 10 years now, and nobody has fixed it. So yeah, just tackling things which are well known for a very, very long time. The biggest issue, and that's also why we think that TTM in its current form is more or less a dead end, are design issues. And the design issue which you can't easily fix, even if it's an internal Linux kernel component with no external API dependencies. The problem here is when you call, let's imagine a user space driver wants to display something on the screen. Not something very unusual, but might happen. So it calls into its driver and says, hey, I want to allocate 3 megabytes of video memory to display something. The driver then calls into TTM, asks for, hey, I need this buffer object backed by 3 megabytes of system memory. TTM then says, oh, I'm running out of video memory, backed by video memory. I'm running out of video memory. Let's call the driver what to do. The driver says, okay, evict some buffers to system memory when you're running out of video memory. TTM then says, okay, I can do that. Let's call the driver to move those buffers. When you want to move those buffers, you're seeing, oh, in my system domain, I'm running out of space. And the driver calls TTM again. And so on and so on. We stumbled over this actually quite a while after taking over maintainership, just by looking at backtraces. When we got backtraces which were like this long, and we are thinking, like, why the heck do we see the driver calling TTM, TTM calling the driver, and so on? And it turned out that that TTM is really designed in the way that your calling path, your call chain, just does a ping-pong between the driver and TTM. Just to make it clear, this is not a recursion. It's just functions calling each other. Yeah, it's good that we had a good piece of kernel stack, because with a 4 kilobyte kernel stack, this would probably overrun your stack, and you got the stack corruption, and that's probably it for the kernel. So yeah. We discussed this internally at AMD quite a bit, and it's a big problem because when, for example, you imagine you add a new structure and want to protect it with a lock. Imagine you take a lock at your driver at the top, and then the driver calls TTM and TTM calls the driver again, and somehow in the middle you need to take the lock again because you don't know who is calling you. That's impossible. That's lock recursion. That won't work. So yeah. One possible solution to that would be to put the whole thing from the head to its feet. So instead of this calling ping pong, TTM becomes some sort of component which just tells you which driver to evict, and then the driver is which buffer to evict, and then the driver is in control of the eviction and no longer TTM, and then you don't need the whole stuff. It needs this recursion anymore. Yeah. How to fix it? What's coming up is to kill TTM. Coming up often is the idea to kill TTM with fire and just write a replacement, and you start to use that in drivers. Turned out that is most likely not a good idea. We've prototyped something like that, or thought about something like that, and for the reason that it's used by many drivers in the kernel, as well as upstream wants a complete solution. David Earlight pretty much said that we want something that works for everybody, and not one memory manager for Intel, one memory manager for AMD, one for the Nouveau guys. We need one common memory manager. So that's actually not going to work. Additional to that, TTM is mostly bug-free by now. over 10 years. I mean, we gathered quite a bunch of dumping stuff, but we also hammered out most bugs in it. So it actually works quite reliable. What we could remove is maybe the AGP support. Hands up, anybody still using AGP gate hardware? I don't think so. Really? Ah, yeah. But you're not using that stuff, so that's not a problem for you. Removing AGP actually won't mean that AGP hardware wouldn't work anymore, because at least the hardware AMD ever sold had not only AGP, but also this internal, how do you call it publicly? I think GPU VM, where page tables are handled like on modern hardware, and the driver is handling the translation tables. So we would just remove the last translation table handling and move that into the driver, and everything should more or less continue to work as it is. Just lose the common AGP translation table management. The next thing which comes to mind is slow decomposition. And that's what we certainly are already doing by removing stuff which doesn't work, which isn't used anymore, and moving stuff which is used but only by one driver into the driver again. That was, like I said, 13% code warp is quite a bit. Then we have, at some point, some locations, we have unnecessary complex handling, because TTM was to some degree meant to do something which is by today's standard doesn't do anymore, managing translation tables. Drivers are managing that, so we could remove that as well, and yeah, goes along with dropping AGP support properly. Last thing on my list here, on that sublist, is moving code into the DMA API. As I said, already discussed it with Christoph Helwig, and I think we have a plan, we just need to implement it. So that is something we will probably do in the next year or so, that we will get with quite a bunch of code here. The last bullet on my list here is moving more functionality into new components. Some guy at Red Hat started with that. Previously, the gem objects, I didn't mention that before. Gem objects are your user space object, user space communication handle with your driver. So what you can think about this is gem is the front end of the driver interface, and TTM is the back end of the driver interface, implementing the backing store where buffers actually are. Previously, it was organized like this, that TTM and gem were completely separated. Recently, somebody of Red Hat gone ahead and made the gem objects a base class of TTM. This has a feature that we can now go ahead and to move duplicate handling. For example, we had for the same buffer objects, we had at least 3 reference counts. One in gem for the handle to user space, one in TTM for the buffer itself, and another one in TTM for eviction logic and list handling. With this move and a bit more cleanup, we can probably go ahead and move all of this reference count into a single one. Will probably make handling quite a bit cleaner and quite a bit easier to maintain. Then what I've already prototyped with Daniel Fedder from Intel as well is a DMA buff locking framework. Basically, when you submit commands from your user space application, something like draw a triangle or draw a square or something like that, you get the commands to draw something, but you also get buffer handles where to draw, what textures to use, what index buffers to use, and so on. Those handles are usually submitted to the kernel in a so-called command submission package. That's more or less the same idea for all drivers, for Nouveau, not Nouveau, for Intel as well as AMD. But what we don't have is a common framework for handling those buffers. Every driver currently implements its own functionality to walk over those list of buffers and stitch together something which then can be given to TTM to move buffers into place, to evict things and stuff like that. So the DMA buff locking framework is a framework based on DMA buff, and then should unify that throughout all drivers, so that we don't need to implement that in each driver separately anymore. So the last thing here is LRU cursor handling. As I said before, during the eviction, TTM is relatively inefficient when it comes to pick which buffer to evict. But it currently does, it always starts at the beginning, then moves over maybe thousands of buffers, which are not valuable for eviction, until it finally finds a candidate and then evict that candidate. And then it starts from the beginning, if that's not enough, to find the next candidate. That is wide out inefficient. So what this LRU cursor is doing is, it instead of getting a lock on the head of the list, of the LRU list, you get a lock on the last item, which is not valuable to evict, and then move on from that to the next item and try to find something which you can remove from video memory and move it to system memory. So, yeah, that's pretty much it. Bit fast. Questions? Questions? Nobody? Yeah, you know.
Okay. Thank you for the presentation.
Sure.
So you have this piece of software that is like old, that has problems, that is used by a lot of people, and you want to change some part of it, and you said earlier that you removed tons of lines of code overnight. How do you deal with that? Like, how do you do changes in an API that is used by so many people? What is your policy?
Oh, good question. So the question, I should repeat it, is how we make sure that we don't break anybody else. Is that correct? Pretty much. Okay. Yeah, first of all, removing the code was pretty easy. You just search if an exported symbol is used by anybody. And if it turns out it's not used, then you can remove the function. That was rather easy. What's more tricky is moving stuff into drivers we don't maintain. For AMD GPU and Radeon, it's relatively easy because we have the hardware, we have CI systems, we have QA, which can look at the code and test it and make sure there are no new bugs by removing or moving stuff around. So that was relatively easy. For VMware, that was relatively easy because we just asked the people to test it. I sent out a patch to Thomas, I forgot his last name. Hellström, yeah. To Thomas Hellström about moving stuff into the VMware graphics driver. And he repeated, oh yeah, good idea, let's do this, but let's do it a bit differently. And you made the typo here, because of that it doesn't work. And based on that, we rather quickly removed or moved code around. What we didn't manage to do is, for example, moving the Nouveau code, because at AMD we don't have the NVIDIA hardware to test that, obviously. And we also don't move around stuff for QXL or other things, while we have some patches regarding that, it's mostly just removing maybe it's 10 lines of code, and that's not really worth it. So, yeah. In general, testing for us happens mostly on AMD hardware. Other questions?
What are the triggers for eviction in TTM, and is there a way for multiple applications fighting for VRAM to crash, or are they going to be stable in a certain situation where they each get their share of VRAM?
Yeah, that's a really good question. So you're basically asking what's the policy and what's how different applications fighting for VRAM are basically going to do. So TTM, the whole idea here is that TTM provides a guarantee for moving forward with a command submission. So if you have sent a list of buffers into your kernel, which you want to have in VRAM, TTM then first of all locks down this list. Those buffers are not going to move then anymore. Then it goes over the list of buffers, and when it finds, oh, something is on swap or something is in system memory, but I need it in VRAM, then it moves in that buffer. While doing so, it can happen that other things are evicted. When in the same time other applications send down requests to move in buffers as well, they start to evict something as well, and then they would wait on that handle to become free. So at some point, you have a guarantee that that you have move forward with some submission. So if you have, for example, 10 submissions, one of them will win and move forward, while others are evicted again and retry, and then you have 9 submissions, and one of them will win, and so on. So it's, in theory, it's guaranteed that command submissions go through. In practice, there's a lot of bunch which can go wrong. That's one of the things which didn't work so well in TTM when we started with it. So.
For example, in Vulkan, you allocate your own memory, and there are ways in which you can have the memory resident or not. If I remember correctly. Anyway, it would be really useful to have some APIs so that the application can know it's running out of memory, and the application can say, okay, I'm gonna reduce my usage. Are you planning anything like that?
Yeah.
Well, but is that actually implemented on Linux at all?
Well, there's a functionality to figure out where a buffer currently is. So if the application is expecting a buffer in video memory, but it was moved out to swap or system memory by the kernel because of eviction, then an application could figure that out. The problem here is that this usually doesn't justify the extra overhead of asking the kernel. So you would need to send a list down to the kernel, hey, give me the location for those buffers. And usually the kernel says, okay, I'm giving you back that list, but till the next command submission, that could have changed already again, and it's actually not that useful. What we do in the AMD GPU driver is we have statistics, how many buffers we have to move around for a command submission. And as soon as applications start to fight for memory, you see those buffer moves go up. And then the application could react and go down a bit. I think the OpenGL driver actually, as Mesa OpenGL actually use that, but I don't think that Redvi or our internal Vulkan driver actually does that.
Question, that you said that there's a way of finding out if it's being swapped out, etc. Is that kernel interface where you find the physical page mappings and you get the bits which tell you whether your pages are dirty or swapped or swapped back, etc.? Is that one?
No.
Okay.
That's what you mean. That's a question about CPU page table mappings. What you mean is that the CPU page table mappings. GPUs, at least our older generation GPUs work a bit differently. They can handle page faults. So you have page tables, but you need to guarantee that those are filled. So you don't have those dirty bits or your swap bits or whatever. So it works a bit different. The latest AMD generation could actually do page faults, but we currently doesn't use it for HMM yet because it's kind of hard to implement.
Getting back to the discussion on memory management and eviction, one of the things that we use elsewhere in the kernel is things like the pressure stall information output. That's what one of the things Facebook added for their servers actually, so that their applications can react when they see that things aren't getting scheduled on the CPU or there's memory pressure on the system. And I think applications like Chrome would definitely benefit from that on the GPU side of things. So if there are OpenGL interfaces that are supported and TTM exposes the right information, then we can use it. But if not, we can add some more. I think that would be helpful. Because I mean, thrashing and eviction is going to...
Yeah, it kills your performance completely. Yeah, exactly.
You definitely want your applications to react and say, okay, I better come down,
right? To repeat the question, or was it a question? I don't know.
Yeah,
Just a statement. To repeat the statement, yeah. Whenever you get into eviction, it completely kills your performance, and completely agree to that. So we actually need to improve both TTM as well as GEM to get rid of eviction situations or to avoid eviction situations, except for things like suspend resume, where you really want to evict everything because it's going to be damaged otherwise. Yeah.
Is there some smarts in TTM to figure out, basically clustering of the LRU? So if you have a large buffer that you want to place in the VRAM, and then you have a lot of small scattered around 4K buffers on the LRU, are you going to evict all of them first and then just figure out, that didn't make any space for my buffer actually? So. Yeah,
your question is how intelligent TTM evicts things, and it's completely brain dead. It starts from the beginning and just evicts until it fits. Yeah. That's not very, very well implemented. That's correct. Anybody else?
Did you ever consider borrowing ideas from the central memory management code, or even having some overlap? Seems like it's the same problem. These things are solved.
What do you mean with central management?
The usual memory management code for Linux.
For the CPU?
That's the same
problems, yeah. Okay, the question is basically, could we reuse more of the core Linux memory management?
Implementation or ideas?
Both, yeah, actually. Yes and no. Yes, for example, in the DMA API, we're actually trying to move functionality there. No, because GPUs, at least the older generation GPUs, work differently than the CPU. As I said, they have page tables, but they don't support recoverable page faults. So at all times, you need to make sure that your page tables are filled from the beginning to the end. One very fundamental idea in the Linux memory management is that at all times you can clear the valid or the read bit or the write bit in your page tables and get a page fault and handle that. This way, for example, is copy on write is implemented in this way. You clear when you call fork, all write bits in your page table are cleared, and the page which you want to access with the CPU is copied, and a clone is created, and the parent uses one copy, the child uses one other one. This won't work with GPUs because GPUs currently can't handle recoverable page fault. For AMD, Vega is the first generation which can, in theory, do that, but they unfortunately implemented only Windows requirements or Microsoft requirements. So the Linux requirements are a bit different, and we actually have a hard time to actually use that hardware in this way.
Eviction strategies?
Excuse me?
And things like eviction strategies or algorithms?
That would probably be something. I think the next big step we are going to use is stuff like memory limits in C group. As I said in
Isn't there even a patch for that?
in this slide, a big reason why we have this mess here is that we, at the very bottom of it, have a limitation of how much memory applications can use. And this is probably better put into C group and into core system memory management. That's definitely the case, yes. 5 minutes left.
Can you elaborate a bit on the differences between Windows and Linux requirements for the
I don't think so. Well, first problem is I'm not an expert on the Windows side. And second problem is I'm not sure if the Windows side isn't under some NDA. I don't know. Oh, somebody else? Okay, that's it.